Hola mates, Captain Jack is back with the theory of PCB traces. This video is the continuation of the theory of the traces studied in the previous video. Now, if you have gone through the designing and the previous theory videos, I have always been warning against taking 90-degree turns on a PCB. So here's the explanation. Imagine driving at 100 miles per hour on a highway and a sudden 90-degree diversion occurs across the road. Either you're one of the lead characters in the racing car movies and you drift the car and survive, or the inertia of your speeding car takes you all the way through the barricades blocking your path. Same is the case with the electrons at high frequency. If the signals have frequencies like radio frequencies, they may radiate at 90-degree turns instead of conducting, and this may lead to signal loss. Though, according to the recent studies, this is a very rare case, but better be careful than sorry. Another reason is that while the older methods of etching were used, it resulted in acid traps. This is a problem related to etching and not a song genre. As the boards were made from a single substrate, this problem may even arise while the separation of boards. The acid puddles are formed at the corners and this can lead to corrosion. Though with most of the advanced technology this problem has been eliminated, it is best to be avoided. The ultimate reason for not keeping the right angle tracks are that do not look attractive. We are used to the 45-degree turns so much that even if we know that right angle turns are safe nowadays, we may prefer not to use them, and I personally would suggest against using right angle turns. So I will just show you an image of how the ideal turns should be to avoid the current drifts. Yes, ironically, the radiation of the currents due to the right angle turns are called current drifts. All these things that are covered are more or less concerned to the EMI, which doesn't mean the monthly installment of the luxurious product bought, but it is the abbreviation for electromagnetic interference in the circuits. It is caused due to various factors which are mostly environmental, and most of them affect the circuit that operate at radio frequencies. Let us understand the bifurcation on a larger scale. Source. Human-made EMI arises from electronic circuits. Naturally occurring EMI, on the other hand, can arise from environmental factors like cosmic noise and lightning. Duration. Continuous interference is an EMI source that emits a constant signal which most often appears as background noise. Impulse interference is intermittent, usually caused by switching systems, lightning, and other non-constant sources. Bandwidth. Narrowband signals like those used by radio can encounter interference from oscillators and transmitters, though these sources only affect certain parts of the spectrum intermittently. Broadband interference affects high data signals like TV and can come from many sources including arc welders and solar noise. We have discussed the various solutions, but let's just revise them. First and foremost being the implementation of planes, maximizing of ground areas, use of solid planes especially in multi-layer PCBs, connect bypass capacitors at the appropriate places, minimal length of signal traces. Then, the trace theory we covered just now. Avoid the use of 90-degree turns, keeping the traces separate similar to the lanes on the highway. Low speed traces separate from the high speed traces and analog separate from the digital ones. Shorter return paths, spacing between the high speed traces should be kept high to avoid capacitance or inductance formation. Similarly, the placement of wires should also be kept in mind. Then comes the placing of the components, which we will cover in the further lectures under the category of the component placing theory. And finally, EMI shielding to the components which may produce EMI, just like Davy Jones who never leaves me no matter what. Now comes the question, what actually is the difference between shielding and grounding? If you were a good listener of my not so boring theory lectures, a big crew would realize the difference immediately. And even though you have figured it out, it's my responsibility to make it clear for you. Grounding is a point in contact with the ground and is a common written in an electric circuit. and an arbitrary point of zero voltage potential. It also provides personal safety and protects the equipment, whereas shielding is the shield which must be connected to the signal reference potential of what is being protected. When there are multiple segments keeping them connected, it is necessary to ensure the same reference potential. The shielding is only efficient when it establishes a low impedance path to the ground. A floating shielding does not protect against interference, which means the shielding should be connected to ground. The use of non-magnetic metals around conductors does not shield against magnetic fields. Basically, shielding is used for protection from interference of another signal such as EMI and external noise. So that's all a person needs to know about the theory of PCB traces. In the next video, we'll observe the selection process of traces and implementation of the same closely. Adios, compañera. Stay tuned.